Welcome, everyone, to the Transforming Power of Software for Autonomous Vehicles. I'm Brent Shedd. I'm the CEO of Zing Robotics, and I'm joined here by Yao Zhai, our head of software and the man of the hour, since we're talking specifically about software. Today, we're going to be using the Zing Robotics eGSE platform, which stands for Ground Service Equipment Platform. This platform is being developed for the tarmac at airports for use by airlines. And the platform itself is electric and autonomous at the level 4 of autonomy. The biggest difference of this platform is that it is natively autonomous. So it's not a retrofit. And since it's natively autonomous, it is software defined. And that software defined nature allows it to function in a variety of different capabilities, and we'll go into more detail about what that entails. But one of those key capabilities is its ability to communicate amongst itself with other Zing vehicles that create a workforce of its own. And so these vehicles have the capacity to operate as a collective, but they also have the ability to communicate with their human co-workers on the tarmac, which is a true inflection point for vehicles, autonomous vehicles and vehicles in general. And it is a critical pathway for adoption of autonomous vehicles going forward. But what's important today is diving into the mechanics of the vehicle and how the software runs the vehicle. And so we're going to have Yao take us through more details on that front.
Thank you, Brent. So as you can see, we are part of the Autoware Foundation, and we are one of the premium members of the foundation. So therefore, we are leveraging the full capacity of the Autoware open source stack that drives the vehicle autonomously. Yeah, so you can see there are 3 stages: the perception, planning, and control phases of the pipeline. The software is also driving a variety of sensors that we are using. As you can see on the right-hand side, we have both 2D and 3D LiDAR scanners. We have cameras, radars, and ultrasonic and GNSS system that are all ROS2 compatible and collecting the sensor data to drive the vehicle and feed into a central computing unit that's manufactured by AD-Link. So we're using the AD-Link computer to crunch the data, and then also runs all the open source components from Autoware Auto underneath ROS2 framework, as well as Cyclone DDS and a few other open source communication modules. We developed our own in-house vehicle interface that works together with Autoware Auto, that works perfectly with our vehicle. I will show you in the next slides. So here you can see this is a system architecture. So in the center you have the AD-Link industrial PC that's driving all of the software components, connected with all the sensors, collecting data, and then generating commands. And then we have developed our own drive-by-wire system that receives the command and drive all the actuators below to interface with our vehicle platform. I want to emphasize that one of our key suppliers, SICK, provided a full range of safety-rated sensors and controllers to make sure that our application is highly safety-rated and meet the standard of airport usage. Here is a view of our own drive-by-wire system. We developed this fully in-house, both high voltage and low voltage power rails, as well as the controllers and software that's running in it. On the right-hand side, however, we're moving towards a more automotive grade controllers developed by ARM. ARM just announced the controllers last month, and as you can see, we will be switching to using ARM-based solutions towards the end of the year. AutoWare AutoStack is fully running on these platforms, and the beginning of next year, the module will also be equipped with automotive safety chips from NXP that guarantees automotive grade and ASIL-D level safety requirements. Hand it back to Brent.
So when we talk about the software-defined nature of the vehicle in terms of capabilities, the use case that we wanted to share with you today is about torque. And today you have different pushback vehicles, and there are different pushback vehicles because of torque. The jets that are narrow body jets need a certain amount of torque from the vehicle to successfully be pushed back and not bend or break the equipment on the aircraft. Whereas a wide body jet requires a completely different level of torque. So that's a completely different vehicle that gets manufactured. And these vehicles cost hundreds of thousands of dollars. Because our GSE platform is software defined, we can adjust the torque through the software. So that allows us to use a single vehicle to push back a narrow body jet, or we can chain a number of vehicles together to multiply that torque and give the vehicle the ability to push back a wide body jet. And because they're software controlled, they operate as a single unit, which, as you can imagine, would be almost impossible in a human operated environment, because the humans would have to be trying to guess what each other is doing. And it would be, there's just not that room for error on the tarmac. Yao really emphasized the safety side of this, and having a software controlled vehicle enables a much higher level of safety for operation, but also for configuration on the tarmac. And that level of configuration extends into a wide variety of use cases on the tarmac, from powering aircraft to perimeter security, clearing foreign objects on the tarmac. Literally, the use cases for a software-defined vehicle on the tarmac is only limited by our human ability to envision what the future of the tarmac should look like. And that's what we're busy doing every day at Zing Robotics. So that is our presentation today. I'm very grateful for your time, and thank you for sharing your time with Yao and myself. If you have questions, we welcome your questions. Just send us an email at info@zingrobotics.com, and we will do our best effort to get back to you quickly. And thank you for your time today. Enjoy the rest of the conference.